Hey everyone, got a few things to cover in this video. I'll start with random variables, and we'll hopefully get a clear answer on what the difference is between being a discrete random variable and a continuous random variable. And once we kind of outline what those mean and what they represent, we'll also calculate the expected value of a discrete random variable. We're not really going to focus on continuous random variables at all today. So again, we'll start off with what are random variables and how do they differ. So a discrete random variable, something that is discrete. I think the best way to really understand what is meant by a discrete random variable is for a variable essentially to be discrete, there are gaps in the values. So these are things that you can really count. Like a decent example, I think, would be the number of students in my classes. I know exactly how many are in my first hour. I know exactly how many are in my second hour, third hour, and so on. So there are gaps in the values. What I mean by that is like on a number line, say, we've got, like I'd have 15 students in one class or 16 students in the other or 17 in the other. There's gaps here. I'm either going to have 15 kids or 16 kids. Maybe I skip a couple to like a class with, I don't know, what would this be, 20 kids. So there's gaps here in between these dots. We can make a dot plot with gaps in between the dots. I'm never going to have like 15.3 students in my first hour class. So again, this was just like my class size. And then the benefit of a discrete random variable is we can assign probabilities to these individual values. For continuous distributions, it's not so easy to do this. Another example, because this is something that comes up quite often, students kind of have a misconception to where they think that anything that's discrete has to be an integer, but that's not entirely true. So like another example could be shoe size. It's entirely possible that, you can have like a size 7, a size 7.5, a size 8, a size 8.5, and so on. Once again, though, maybe I have a student that wears a size 7 shoe, a student that wears a size 7.5 shoe, and like 2 students with a size 8 shoe. Again, there are gaps in between the 7 and the 7.5. Nobody's going to fall within this range. You buy a shoe, it's either going to be a 7 or a 7.5. So even though it's not an integer, it still is discrete. All right, so continuous then, of course, is just the exact opposite of that. Continuous random variable. I like to think of it as these types of variables cannot be measured precisely. So I think my favorite example for this is the length of the California coastline. It opens up to the Pacific Ocean, but you'll never actually know the length of the California coastline because it's constantly changing. High tide, low tide comes in probably like more often when the moon's in a certain position or whatever, but you're never going to get the exact length of the coast. Again, it's always changing. We're never going to know the exact length of that coast. You can always make it a little bit more precise. How you would model this is probably a distribution, not like this, but something maybe more normal, right? You might have to fit a bell curve to it to get the average length of the California coastline. Another example, going with what we did up here maybe, is instead of shoe size, something that would be continuous could be foot length. We can have someone that has like a foot that is 9 inches long, someone that's 10 inches long, someone that's 11 inches, 12 inches, 13. And then if I round to get to these 9, 10s, 11s, and 12s, we can absolutely have somebody with a foot that is like 9.8 inches long. And then we can have somebody with a foot that is like 9.82 inches long. Depending on who measures it, it can vary between the measurements. And this is all something that is continuous, continuously getting more precise. You're never actually going to get the exact measurement, but you get closer and closer the more accurate that you're trying to get. So hopefully that clears up the difference between discrete and continuous. Discrete, there are going to be gaps in between the values. Like I said, with class size, I can't break this down to like 16.3, but in this little dot plot that I started creating down here, we can absolutely have a value like right here, a student with a foot that is 9.4 inches long. Okay, we'll talk more about this entire unit, but a random variable, it has probabilities for certain values depending on how likely that value is to occur. So I got an example down here that might help clear this stuff up. Again, we're only going to focus on discrete random variables today. So the expected value for a discrete random variable. I've got the example all set up. If you need to pause the video and like write this down, might be a good idea. You can refer back to it later. But I've got some information here on a high school in Nova Scotia where X is the number of snow days, and we've just got the distribution of it here. So one thing I wanted to make clear with this distribution is it's a random variable, but it's still just a probability distribution. So these probabilities, each individual probability, that's what's meant by the I, has to be between 0 and 1. Still follows our basic probability rules, and all of these outcomes added together have to have a probability of 1, or like 100%. And then these distributions are really easy to interpret and read, I think. So we've got the value of every individual observation. It's discrete because we're either going to have 1 snow day or 2 snow days. We're not going to have 1.789 snow days at this one high school. So this value, for instance, represents 1 snow day. The probability that the school has 1 snow day throughout the year is 0.19, or essentially a 19% chance of having 1 snow day. And you can see as you read down this, those probabilities decrease, and there's only a 1% chance of having 10 snow days. Okay, so let's just use this discrete probability distribution to find some probabilities and calculate the expected value. Okay, so find the probability that the school has 0 snow days. Now we're going to write this in terms of our random variable. So really, the big difference here is we're doing it in terms of this random variable and not an event. We are really just going to write our probability statements, pretty similar to what we did in the last section, but instead of just like the probability of event A or event C, it's the probability of our random variable X being equal to 0. And just like we did in the last section, we know that the probability of X is equal to 0 would just be equal to 1 minus this probability. So, or I should say that wrong. 1 minus the probability that this doesn't happen, that complement rule. Remember the complement rule, we put like a little C there? Maybe I'll write it out like this. It's equal to 1 minus the probability that X does not equal 0, but that event or this random variable's value does not occur. So let's go ahead and figure that out. 1 minus, to get the probability that it's not equal to 0, of course, we'll just add together all of these probabilities. So I'll get out a calculator for that. 0.19 plus 0.14 plus 0.10 plus 0.07 0.05 plus 0.04, 0.02, And then I have 0.01 two times at the end. Okay, I'll hit enter and we get 0.63. So all of these probabilities added together are 0.63. So the probability that x equals 0 is, well, 1 minus 0.63. And we get 0.37. 0.37. I feel like I might have missed something. 19, 14, 10, 7, 5, 4. Yeah, I missed a 4 right there. We add 1.04. Do that subtraction one more time. So 0.33. So 33% chance of getting 0 snow days. I'll put that in my table up here. 0.33. So that should be very similar to you, like no difference in what we did in the last section. We looked at a couple with like rolling die, and the same concept really applied. You have the events up here, the probabilities down below, and they all had to add up to 1. Okay, question 2, find the probability that the school has to make up snow days at the end of the year. So it kind of cuts into their summer vacation a little bit. They're allowed 5, so as long as they have 5 or fewer, they don't have to tack on extra school days at the end of the year. So they're allowed 5, which means we're trying to find the probability that x is greater than 5. X is greater than 5. So we would be adding together. It's greater than 5, so we don't want to include the 5 here. They can have 5 snow days and not have to make up anything. So I'll add 0.04 to 0.04 to 2 to 0.01 and then 0.01 again. So 1, 2, 3, 4, 5 values I'm adding down here. Okay, so we got like 8, 10, 11, 12. So 12% chance that they have to make up their snow days at the end of the year, at least one. Okay, very good. Most of this should be a review. It's just a little bit different the way that we're writing these things. So number 3, find the expected value for the number of snow days in any given year. So to do this, we actually have a formula to do it for any random variable, not for any, for any discrete random variable. The expected value is, so here's the symbol for it, the mean. The mean is really interchangeable with expected value in this case. The average snow days that we're going to have, the mean of x is equal to the sum of each value multiplied by each of its corresponding probability. That's it. That's the formula that you need to use to find expected value. So you would be doing, in this one up here, the mean for the expected number of snow days is equal to, well, we just take our first value, multiply it by its probability. So 0 times 0.33. And then add, because let's remember what sigma means, it's really just the sum of each of these things, the sum. So then we'll add the next value, which is 1, times its probability of 0.19. And that just continues. So plus 2 times 0.14, plus 3 times 0.1, or 0.10, and then on and on and on. So I'll just type that all into my calculator to get it all in one go. Should be able to see. So I'm not going to do 0 times 0.33 because we know that's 0. And 1 times 0.19 is just going to be 0.19. Do all the rest though. So I'm doing 2 times 0.14 plus, next I have 3 times 0.1 plus, so very easy thing to do just kind of a long drawn out process. Then 5 times its probability is 0.05 plus 6. Probability to have 6 snow days is 0.04. All right, almost done now. Plus 7 times 0.04 again, plus 8 times 0.02, 9 times 0.01, and finally 10 times 0.01. Okay, and there are our expected number of snow days, 2.17. So 2.17 is the expected number of snow days we would have in any given calendar year. Not calendar year, school year, academic year, I should say. And that's it. So to get the expected value or the mean of a discrete random variable, just multiply its value by its associated probability. All right, this video has gone on long enough, I think. Thanks for watching. See y'all in class. Bye-bye.